Okay, today we talk about section 3.4. This is composition of functions. We're going to learn how to compose functions. But before we do that, we need to know about the operations. Of functions. And we've done this before. The operations are adding, subtracting, multiplying, and dividing. Okay, those are our main operations. So recall you could add two functions. Okay. So we could add a function f and add it to g. Okay. And a new notation for us to write that is I could take f plus g of x. So this is f plus g of x. Okay. This does not mean multiply by x. Okay. Just like this is f of x and this is g of x, this means f plus g of x. It means this. Okay. Similarly with the subtraction, if we do that, remember we're going to have to distribute through here. But the new notation is this. And we read this f minus g of x. And the result here will be a new function. So that's good. When we add two numbers, we get another number. When we add two functions, we get a new function. We can also multiply functions. And the new notation here is f, and then this is a little dot, okay, that's filled in, like so. And this is read f times g of x. Again, not multiplying by x, it's of x. Now we could also take two functions and divide them. If we do that, we have to remember that the denominator can never equal 0. And the new notation for that is f divided by g of x. Okay, and now, since these are new functions, we have to worry about the domain. And so we'll note that the domains of these functions consist of all x, our independent variable, our inputs, in the domains of f of x and g of x. That is, another word for that is the intersection of the domains. Okay, so let's do some examples. So for example, if we have f of x is equal to 2x minus 5, this is a simple linear function, so we know the domain here is all real numbers. Now for g of x, we have x squared plus 3x. This is still a polynomial function, so its domain is all real numbers. So now let's find f minus g of x. Okay, so f minus g of x. Alright, well I always just like to write out what that means. That means we're going to take f of x and subtract g of x off of it. So f of x is 2x minus 5. This is f of x. And then we need to subtract from the formula. And then I'm going to open up parentheses because remember when you're subtracting two functions, you have to distribute. And g of x is x squared plus 3x. Okay, so this is g. So just copying the 2x minus 5, I need to distribute this negative through. And then we can just combine like terms. X squared, negative x squared is the first. We have 2x minus 3x, which is minus x. And then we just simply have the minus 5. Okay. So this is the new resulting function. This is f minus g of x. It is a polynomial, and its domain is negative infinity to infinity. It is all real numbers. We could multiply f times g of x. And again, I just write down what that means. I'm going to take f of x and multiply it by g of x. So f of x, we said, was 2x minus 5. And g of x was x squared plus 3x. Now we'll multiply this out by foiling. Okay, so we'll get 2x cubed plus 6x squared minus 5x squared minus 15x plus 6x minus 5x minus 15. Then we can combine these like terms. So our new resulting function is 2x cubed plus x squared minus 15x. This is f times g of x. It is a polynomial, and its domain then is all real numbers. Okay. It's a polynomial because all of the exponents are 0 or positive integers. Now things will get a little different when we divide. If I wanted to find f divided by g of x, remember what that means. We'll take f of x and divide it by g of x. But now this is a rational function, so we know that g of x cannot equal 0. So let's look at it. F of x is 2x minus 5, and we divide that by g of x, which is x squared plus 3x. Okay. Now if we factor this, it'll be very easy for us to see what values of x will make the denominator go to 0. There's a common factor of x in both of these, so I could factor them out and get x times x plus 3. And then it's very clear from here that if x equals 0, we get a problem. Or from this factor, that if x equals negative 3, we get a problem. Okay. So now the domain of this function is a set of all x such that x cannot equal 0 and negative 3. Okay. So this is the domain of our new function. Okay, but we've been doing things like this. Okay. What we might be worried about now is a new operation. Okay. And that new operation is composition of functions. Okay. So let me show you the notation. Composition notation says you'll take F and then you put an open circle. Okay, this does not mean multiplication. This means the composition of G. Okay, so F composed with G of X. Okay, so let's write that down. F composed with G of X. And what that means is when we compose two functions, okay, F is our outside function, okay, and now as opposed to having the input of F be X, the input will be the entire function G of X. Okay. This is our new input. Okay. And sometimes it gets written much smaller like this. I'm just trying to overemphasize what the input is. And we also have to be concerned about domain here. So the domain is all values of X in the domain of G, okay, so G is the inside, such that G of X, okay, so whatever we put in, G of X, has to be in the domain of the outside function. So such that G of X is in the domain of the outside function, which is F. And we're going to practice this. This is going to take a little bit of practice to get used to what's happening here. Okay. And you can compose more than one function. That's not a problem. Let's do an example. Let's say we have f of x is equal to 3x plus 5, and g of x is equal to the square root of x, and h of x is equal to x squared minus 2x. Okay. Let's find f composed of h of x. So I always like to write what this means. F is the outside function, and into that I'm going to put h of x. So that's the same thing as f. Well, what am I putting into f? I'm putting h, which is x squared minus 2x. And now that is what's going into f. So f has the form 3 times x plus 5, but we're not putting in x, we're putting in the entire function h, so it's x squared minus 2x. And now we can simplify this. Let's distribute this 3 through. So we'll get 3x squared minus 6x, plus 5. And this is our new function, f composed of h. Now what we put in to f was h, and it has a domain of all real numbers. Okay, so there's no restrictions there. And what comes out is a polynomial, so there's also no restrictions. So the domain is still all real numbers. Now we could do it the other way. We could take h and compose it with f of x. So that would mean now that h is the outside function, and what's going into h is f of x. So it might be easier to say it than this way. F of x is 3x minus 5. No, plus 5, sorry. Okay. Now h has the form x squared minus 2 times x. That's the form of h. But what we're putting into h is the entire function of f. Now let's simplify that. Okay. Remember, this squaring means we'll take 3x plus 5 times 3x plus 5. And while we're at it, we may as well distribute this 2. And remember to take the negative with it. So that's minus 6x minus 10. We'll continue to simplify. So this becomes 9x squared plus 15x plus 15x plus 25, and then we'll just bring down the minus 6x minus 10. Okay, let's combine some like terms. So 9x squared stays by itself. Okay. Here I have 15x plus 15x, which is plus 30x, but then I'm going to subtract off 6 x's. So I have plus 24x. And here if I have plus 25 and I subtract 10, I have plus 15. So this is our new function, h composed of f. What we put in was a polynomial and has no domain restrictions. When we finish, this is a polynomial and has no domain restrictions. So the domain for our composition of our composed function is negative infinity to infinity. And let's put a star by this because we're going to come back to this result in just a moment. Let's do another. Let's find g composed of f of x. So we're going to take g, and into g we'll put f. So that is g composed with f, which is 3x plus 5. Okay. Now, what is g? Well, g has the form the square root of x, and what we're putting into that is 3x plus 5. And that's it. There's nothing we can simplify here. That is g composed of f. But what about the domain now? Into g I put f, which is a polynomial, and its domain is all real numbers. So for f of x, the domain was all real numbers. But when we look at this now, we no longer have a polynomial. So we know that the domain for the composition is that this, whatever's underneath this radical, has to stay greater than or equal to 0. So 3x's has to stay greater than or equal to 5, negative 5. And then x has to stay greater than or equal to negative 5/3. So if we wrote that in interval notation, we go from negative 5/3 included, because of the equality, up until infinity. So this is the domain of the composition. Okay, let's go the other way around. Let's find f composed with g of x. So that means into f we're going to put g of x. So that is f, and g was the square root of x. Okay, so we're going to compose that with the square root of x. Now f has the form 3 times something plus 5, and that something is the square root of x. Which we could just simply write as 3 square roots of x plus 5. Now, with the square root of x, our domain goes from 0 inclusive to infinity. And for our new function, it turns out that is the restriction as well. Because if x goes negative, this entire function goes undefined. So this is the domain of our new function. And now we can compose multiple functions at a time. It's no problem. We could take g and compose it with h, and then compose that with f of x. So what that means then is g is the outside function, and into that I put h, but what I've put into h is f of x. Okay. Now the nice thing is that we've already found h composed of f. Okay, we did that back where I had you make a star. Okay. So that is really g composed with 9x squared plus 24x plus 15. Okay. And then what is g? Well, we have to put this into g, and g is the square root, and then putting this in at 9x squared plus 24x plus 15. Now in this case there's no restrictions. This is a polynomial, so there's no restrictions on what we can put in. However, in this composition we now have a problem. This has to stay greater than or equal to 0. And the trouble is that this is no longer linear, so we cannot just solve 9x squared plus 24x plus 15 as being greater than or equal to 0, because it's not linear. Okay. Remember, this is going to be some type of parabola. Okay. So there's going to be certain values for which it's greater than or equal to 0. So remember, this is the case where we're going to use our test point method. We're going to find our critical values. That is, first we have to solve the equality to get these critical values. Now, there's a common factor of 3 in all of these, so let's divide out that 3 to make this a little simple for us. And the great thing about that is that 0 divided by 3 is 0. This becomes 3x squared plus 3 goes into 24 8 times plus 5. Okay. Now I bet this is going to factor. Okay. To get to 3x squared I need a 3x and an x. To get to 5 I need a 1 and a 5. But if I put the 5 here, I'm going to get 15x, which is much bigger than 8. So let's put the 5 here, the 1 there, and we'll do pluses, because we have 2 pluses. So 3x squared plus 3x plus 5x is plus 8x plus 5. So we're good. So our critical values are either that 3x plus 5 equals 0, so x is equal to negative 5 thirds, subtract 5, divide by 3, or that x plus 1 equals 0, so that x is equal to negative 1, these are the critical values. Okay. Now, what we do with the critical values, once we've found these, then we have to put those on the number line. Because we're trying to test the domain. So this is negative 5/3, and this is negative 1. And we have to pick values that are in between there, in each of the three intervals. So the easy one here is 0's in there. We could pick, let's see, negative 6/3 would be negative 2, so let's pick negative 2. And there's really nothing too easy in here. This is negative 3/3, this is negative 5/3, so negative 4/3 is inside there. Okay. Now, we want to know, we want to test each of these. Okay, so we're negative 2. Okay. We have to put that into the original. So 9x squared plus 24x plus 15. And we want to know if that's greater than or equal to 0. Okay. So we're testing negative 2. So let's find out. Okay. This becomes 9 times positive 4. Then we're minusing 48 and adding 15. So this is 36 minus 48 plus 15. Alright, 48 minus 36. 2 is 12, okay, but the 48 is larger, so is minus 12 plus 15. Is that greater than or equal to 0? Yes, this is true. Okay. So it is true on this interval. And since we're looking for equality, we can also include this point, so it's true down this way. Now, let's look at negative 4/3. Okay, so again, our form is 9 times something squared plus 24 times something plus 15. Is that greater than or equal to 0? Okay. So we'll put in negative 4/3, negative 4/3. So this becomes 9 times, squaring this, the negative will become positive, 4 becomes 16, and 3 squared is 9. Now here, you can think about this as over 1. Okay. We have to take this negative, negative and a positive will be minus. Now 3 goes into itself once, and it's 24 8 times, and 8 times the negative 4 is minus 32, plus 15. We're still wondering if that's greater than or equal to 0. Here this will cancel, so remember that's like 9/1. So we're left just with the 16 minus 32 plus 15. This becomes minus 16 plus 15, and is minus 16 plus 15 greater than or equal to 0? No. Negative 1 is not greater than or equal to 0. So it is false. So it is false on this interval. Now, let's look here and test 0. Okay, so with 0, the form is 9 times something squared plus 24 times something plus 15. So what we're testing is 0. The great thing about 0 is this becomes 0, this becomes 0 plus 15. Is that greater than or equal to 0? Yes, it is true. So it is true on this interval. And we have the equality. We can circle this in because of our original less than or equal to. And now we know the domain of our function, of our composed function. So this is negative infinity. So the domain goes from negative infinity to negative 5/3. We can include that because of the equality. And then it's true again from negative 1 up until infinity. So this is the domain of our composed function. Okay, so that's how you compose functions. We'll look at some more examples in a little bit about the domain and how to find domains when you're composing other functions. Okay, so this was just a start. And I think the fun part about composing functions is learning how to decompose them. Okay. So, what's helpful about decomposing functions is it allows us to take more complex functions and simplify them into basic parent functions. So let's say we have f, and that's one of our parent functions, the cube root of x. Let's say we have g, and this is a simple linear function. It's just the our identity function shifted up 4 units. And let's say we have h of x, which is 5 times x. So this is our basic identity function just with a steeper slope. Okay, so these are our basic parents. Now let's say I have a function f of x that is the cube root of x plus 4. Okay. This is a more complex function than either of these. But I can decompose this into these basic parent functions. Notice what we have here, x plus 4, is g of x. And what we have outside of here is f of x. So really, if we take f and we compose that with g, that would be our capital function f. And the way we could write that then is f composed of g of x. So I can think about this more complicated function in terms of 2 smaller, simpler functions. Let's try another one. Let's say I had 5 times the cube root of x plus 4. Well, we have to start breaking this down. Okay. I do see this cube root function there. I do see this plus 4, which is kind of making me think of this. And then we also see this 5, which is making me think of h. So I'm thinking it's going to take all 3 functions for us to rewrite this. The question is, in what order? Let me give you a minute to think about that. What must be the innermost function that we'll put into the next and into the next? So I'm thinking the innermost function must be our cube root, which is f. And where do I want to put that into? Well, I need it to be multiplied by 5, so let's put that into h. So So that would give me 5 times the cube root of x, and now I need to add 4, so that would need to go into g. Which we could write as g composed with h composed of f of x. So let's make sure. So f, the cube root of x, goes into h to get 5x cubed. And then we need to add 4 so we can put it in there. Let's say we have this one though, 5 times the cube root of x plus 4. I'll give you a second to think about it. Okay, so inside here I see g, I see the cube root, which is f, and I see 5 times something, which is h. So let's start with this time g, and into g I want to put it into the cube root, so I need to put that into f, and then I need it to be multiplied by 5, so let's put that into h. So let's just double check. G of x goes into f would be the cube root of x plus 4. That's good. And then I need this all multiplied by 5, so that's h. So this is h composed of f composed of g of x. Now, h of x, this is a deceptively simple one, okay? So this is just our basic identity function shifted up 12 units. You wouldn't really need to think about this in terms of the composition, however you could. I hope you'd agree this, that I could write x plus 12 as x plus 4 plus 4 plus 4. Why I think about that then is I could associate these first. Okay. This would be g of x. And then I'm going to add 4 again. Well, that's another version of g of x, right? And then I'd have to add 4 again. So what's really happening here is that this is really... I'll take g and then put it back into g for this one, and then I have to put it back into g for that one. Okay. So in this way, I'm composing a function with itself. So I have g composed of g composed of g of x. Now that's perfectly fine to compose a function with itself. When doing that, you're just asking, what if I take this rule or this function and this process and I keep repeating it over and over and over again, what will be the result? Okay, so those are fun. Right? And I think pretty easily attainable, and they'll be very helpful. Decomposing functions is going to be very helpful to you in calculus when you start using a thing called the chain rule. Alright, let's look at some more difficult examples about how to find domain of a composite function. Okay, we did some nicer, simple examples with the polynomials, but things get a little more confusing. Okay. Composition of functions. Alright. Let's do one where we have radicals. Okay. Or, I'm sorry, rationals. Let's say we have f of x is equal to 5 over x minus 1, so a rational function. And g of x is equal to 4 over 3x minus 2. Okay. And what we want to find is f composed of g of x. Alright. Let's find this first. Okay, well, first let's state domains. Okay. We know that 3x minus 2 cannot equal 0, so x cannot equal 2/3. Okay. Adding 2 and dividing by 3. Okay. For g. And here we know that x cannot equal 1. Alright, we'll come back to that. Now let's find f composed of g. That means I'm going to take f, and into it I'm going to put g. So I'm going to take f, and into it we put this entire function, 4 over 3x minus 2. Alright, so let's do that. Let's do it over here. So here's f, 5 over something minus 1. But our something is the entire function g, 4 over 3x minus 2. Now we need to simplify this. So remember, let's think about this as 1 over 1. We're subtracting fractions. And when we do that, we're going to need a common denominator. So this is 3x minus 2. So our numerator stays the same, which is 5. But now our common denominator is 3x minus 2. And then we have the 4 minus 1 times 3x minus 2. Remember to use your parentheses because we need to simplify by distributing. So this is 5 over, okay, our common denominator stays the same here, 3x minus 2. So this is 4 minus 3x plus 2. All right. Good. Now we're still not simplified. Okay, we're dividing, so let's write this as 5 over 1. And remember that when you're dividing fractions, it's the same thing as inverting and multiplying. And let's simplify this. 4 plus 2 is 6 minus 3x. Now there's no common factors, and I could just leave it factored because we're really just looking for the domain here. Well, we found the composition. Okay, so this is the composition. You could multiply this out and say that's 15x minus 10. That's no problem. Or you can leave it this way. Okay. Alright, now from here, we're concerned about the domain. So we know that the denominator, 6 minus 3x, cannot equal 0. So 6 cannot equal 3x, or that x cannot equal 2. But, and we might think that's the only thing, okay? That this is the only restriction. However, we have to remember what we put into f was g, and g has its own restrictions. Okay. From g, we see that x cannot equal 2/3. Okay. So we have to have the intersection of both of these. Okay. We also have to have this. If I'm going to put g in, I can't put in 2/3, but I also know that I have to throw out any values where g equals 1, because that's the restriction of this. So let's do that right now. Let's find out, okay, let's write this down. Since f of x cannot equal 1, and we're putting g goes into f, then g of x can also not equal 1. So let's solve that. G of x is 4 over 3x minus 2, and that cannot equal 1. Remember, that's like over 1 if you want to think about it that way. You don't necessarily need to. Let's multiply both sides by 3x minus 2. So these will cancel. Then on this side we'll have 4 is equal to 3x minus 2. Adding 2, we get 6 is equal to 3x. So x cannot equal 2. Which was the same value as the domain that we found here. Okay, so we don't have to exclude a third value. So our total domain for this function is the set of all x such that x cannot equal 2/3. Because if x equals 2/3, the inside function goes undefined. Okay? And then x cannot equal 2. So this is the domain of the composite function. It is the intersection of all of the two. Okay, let's do another example with radicals. Let's say f of x is equal to square root of x plus 2, and g of x is equal to the square root of 3 minus x. And let's find f composed of g of x. That is, I'm going to take f, and into it I'm going to put g of x. So f is the square root of something minus 2. Is this the way I want to do that? Square root. I want this to be x squared. Okay, so now we have to take g and put into this. Okay, so g, so this, okay, the form of x is the square root of something squared plus 2. Okay. And into that I want to put g, which is the square root of 3 minus x. Okay, so this is equal to, now the square root and the squaring will undo each other, 3 minus x plus 2. So this is the square root of 5 minus x. Okay. This is the composition. Now we know from here that what's underneath the radical, 5 minus x, has to stay greater than or equal to 0. Okay. So we know that 5 has to be greater than or equal to x by adding x to both sides, which is the same thing as saying x is less than or equal to 5. And again, we might be tempted to say that this is the domain. However, we have to take into account any domain restrictions for what we put into it. Okay? So if we look at the domain restrictions for g, we know that 3 minus x has to stay greater than or equal 0. So 3 has to be greater than or equal to x, so x has to be less than or equal to 3. Now this restriction has to meet that restriction. Okay. So our input, let's do this in orange. So our input, x has to stay less than or equal to 3. Now from here, we would say x has to be less than or equal to 5. But we need the intersection. We need it where it is both true. That is where they both have values. So they both have values all the way up to and including 3. Okay. So that means the domain of our function is not x less than or equal to 5. It is negative infinity to 3 inclusive. Or, let's see, what is this? X less than or equal to 3. Okay. These are the actual, is the actual domain, okay, because it has to match. Okay, let's try a more difficult one. Let's combine where we have a rational and a radical. So let's say f of x is equal to 1 over x minus 2, and g of x is a radical x plus 4. And we're going to find f composed of g of x. So f, we'll take f and into it we're going to put g. Now, we know from here we have x plus 4 has to be greater than or equal to 0. So x must be greater than or equal to negative 4. We also know from here that x cannot equal 2. Before we find this, let's keep working with the domain. Well, let's find it and then we'll work with the domain. Okay, so f is 1 over x minus 2, but what we're putting in for x is all of g, which is the square root of x plus 4. And there's nothing you can do to simplify this. We could rationalize the denominator and multiply by this conjugate. Let's do that. That's always a good thing to do. On your exam, I'll take this, but we need to practice rationalizing. Okay. All right. So to rationalize, we need to multiply by the conjugate, and the conjugate is where you keep the two terms the same. Okay, but we're going to change the sign in the middle to the positive. Now, the numerator is going to stay the same because 1 times anything is anything. Square root of x plus 4 plus 2 over. Now, the square root of x plus 4 times the square root of x plus 4, that's the square root of x plus 4 squared. Then plus 2 times the square root of x plus 4 minus 2 times the square root of x plus 4, and then minus 4. So from here, the numerator will stay the square root of x plus 4 plus 2 over. Now the square root of x plus 4 squared is just x plus 4. This will cancel with this, and we have just minus 4. And we have the square root of x plus 4 plus 2 all over just simply x. From here we can see that x cannot equal 0, and from here we have that x has to stay greater than or equal to negative 4. Okay. So let's see how that works if we had come up with it this way. Okay. So we know from the beginning our input is that x has to stay greater than or equal to negative 4. Okay, that's good. It's represented here. Okay. From here, we see x cannot equal 2. So where does that x equals 0 come from? Well, remember, we're putting g of x into here, so we have that g of x cannot equal 2. Now let's solve that equation. So g of x is the square root of x plus 4. It cannot equal 2. If we square both sides, this will become x plus 4 cannot equal 4, or that x cannot equal 0. Okay. So in this case, both of them came out. Okay. So how should we write that? Well, if we had to do it in interval notation, let's draw a picture to make it clearer for us. Okay. So x has to be greater than or equal to negative 4 all the way. Here's 0. It can't equal 0, and then we'll continue on. So we have two intervals. This first one goes from negative 4 all the way up to 0, but can't include 0. The second interval starts at 0 and goes all the way up to infinity. So this is our domain. Okay, so that's as difficult as the homework's going to get, is determining these ranges. So please make sure that you're clear on what we're asking, and then the math can follow from that. Okay? So email me if you have a question.